Welcome, everybody, to Bitwise Day. Bitwise, of course, being the name of the infamous Fresno tech hub that collapsed rather spectacularly within the last year. This is, by the way, not a beer. This is liquid death. It looks like beer, but it's water, in case you're wondering what was in my background there. Not that there's anything wrong with beer, but yeah, I don't drink when teaching. So this is Bury It Alive. It is a berry flavored water, non-alcoholic drink. Mm. So Bitwise, for those of you that don't know, was run by Jake Soberall and Inga something or other. And basically, they were a tech hub where, like, if you're an independent contractor, you could rent a cubicle, high-speed internet at a fairly cheap rate. They had Friday get-togethers where potential employers, potential employees would come and mingle and meet each other. They did education, they did boot camps, they placed people with internships. But really, they were a real estate company. And the reason why they collapsed was because they were like in a joint partnership. Like most of their buildings were independent corporations, they were joint partnerships. And they put up those buildings as collateral for other loans, allegedly, without the permission of the people who actually owned it. And so Jake is, I don't know, probably going to go to jail. I've met him, talked to him before. I've invited Bitwise out, but they're gone now. And the people that came out to speak today, which was let's see if I can pull this open on here. These guys came out today. Cotman, they do a lot of IT stuff. One of the owner of the company actually was the property manager for South Stadium after Bitwise died for a couple weeks, as he's based out of down there as well. Okay, so topic today: Bitwise, not just Bitwise Industries, Fresno local scam artists, but but it's a thing, okay, where you work directly with ones and zeros in your code. And so my mom always says, my son works with ones and zeros. Like this is what I stare at all day long, just ones and zeros. And it's like, yeah, no, not really. Like, I don't. Yeah, no. Can if I want to, but it's very, very slow and very tedious to work with ones and zeros. Usually, we operate at a higher level, and like we talked about last time with Huffman coding, though, if you do kind of get down to the bit level, you can actually try to make your code more performant, especially in terms of bandwidth, than if you just don't care. So once during the .com boom, I was working for the San Diego Supercomputer Center, and they couldn't hire computer science people to save their lives. Like computer science majors were getting like, oh, you're a junior, come work for us for 170 a year. Like it was crazy. It's just everyone's like leaving the department left and right. Everyone's getting jobs. Poor old San Diego Supercomputer Center is trying to hire a manager, and so they had to hire like a physics guy who had like taken a programming class once, and he's trying to manage me, and he has no idea what he's doing. So he's like, I don't like the fact that you've written your own protocol between the client and the server that packs all these things down very tightly and very quickly transmits the files to each other. Everyone these days, from what I've read, is using XML. You should use XML so that it's interoperable. I'm like, with who? I wrote the client, I wrote the server. We don't talk to anyone else. We don't need to make it interoperable. An XML page is going to be probably 4 or 5 times the size of our file, maybe bigger, maybe an order of magnitude bigger. It's absolutely absurd. And if you look at how modern first-person shooters are, they just don't care about compressing, the network traffic down as much as they used to. Quake, the original Quake, somehow ran over a 14.4 modem, ran great over a cable modem, with 32 players running at very high speeds. Nowadays, first-person shooters, you walk through mud. If you're a Halo super soldier, you can run for about 3 seconds at what I would consider like a normal walking speed in old first-person shooters. And Overwatch used to have 6v6s, and now they're 5v5s because they can't probably handle 12 players, right? Whereas Quake had 32 people in it. So I do think these kinds of things we're talking about today here is a little bit of a lost art, but it shouldn't be, because these kinds of things actually crop up everywhere. If you look at the code for like opening a file, so if you open a file, this is how you open a file in Linux. The ifstream library is a wrapper around it, but the way that you actually open a file in Linux is with the open call, believe it or not. And the open call takes in an integer called flags. And so flags is a 32-bit number, right? Full of ones and zeros. A 1 means the flag is set, the Boolean is set. A 0 means the Boolean's not set. So this is our last data structure for the semester, probably. We've done arrays, vectors, decks, linked lists, stacks, queues, binary search trees, heaps, hash tables, tries, and the very final, very ultimate data structure, integer, int. Int is the last data structure. There you go. Int. It's a data structure. It's 32 booleans all at once. And what's really cool about it is you can actually do 32 sets, 32 deletes, 32 searches, all in parallel, all at the same time in a single operation, which is pretty cool. You also don't need to pass in 32 different booleans here. You pass in one boolean, and that is 32 parameters all at once. And these flags things here are things like directory, no kitty, no follow, temp file, truncate, create, flow exec, read write, somewhere in there. Yeah. So there's all sorts of flags that you can pass in: direct, desync, execl, large file, whatever. No kitty, no follow. Yeah. So there's all these things, and all of these things are powers of 2. And the reason why they're powers of 2 is because if you look at binary numbers, if you have a binary number like 1101, the last one here is the 1's digit, that's the 2's digit, that's the 4's digit, that's the 8's digit. And so the number 8 corresponds to the 4th bit in the bit field. The number 4 corresponds to the 3rd bit, so on and so forth. So what you do is you set up your thing such that everything is a power of 2. Oh, this is the wrong one. Bitfield. Yeah, there we go. There we go. So you set up your thing so that everything is it's a different inventory assignment. You set up everything so everything is a power of 2. So if you're picking up the red key is bit 1, the yellow key is bit 2, the green key is bit 4. Thus, the first bit in the integer, if it's true, that means you have the red key. If it's false, you don't have the red key. If the second bit, the 2's bit, is true, you've got the yellow key. If it's false, you don't have the yellow key. And so you can have up to 32 different keys picked up or not picked up. And if you want to send the state of that to, a client over the internet, you just send a single integer to them. You've just transmitted 32 different true or false values. Do you have this or do you not have this? And you can do this for weapons as well. So if you want to send out which weapons you have, the 1's bit is the grappling hook, the 2's bit is the Navarro, the 4's bit is the medikit, so on and so forth. And so you just assign a meaning to each one of the bits in an integer. And if that bit is true, then congratulations. Like if where's the rocket launcher? If the 8192's bit is true, congratulations, you have the rocket launcher. If it's 0, you don't. You guys understand? And so this allows you very quickly to send an update to people. Hey, that guy over there, here's all the weapons he has. 1 integer. Done. Right? And you get a complete update of his entire inventory, as long as the inventory can be represented in true and false values. This doesn't work nearly as well with games like Borderlands, where all the weapons are sort of randomly, rolled and smushed together and things like that. You need to send a little bit more information like that. But it works great for games where you just either have an item or you don't have it. And it allows you to minimize the number of bits you're sending. Last time, we talked about Huffman coding. Huffman coding, you turn a letter, like A or E or whatever, into bits. True, true, false. False, false, true, true, false, whatever. And with bit packing, bitwise operations, which is what we're talking about today, you can actually figure out how to actually put all those bits together into a bit field and then transmit that in a compressed fashion. So a character is 8 bits. A character is always a byte. Definitionally, a character in C++ is a byte. And bytes are almost always 8 bits. They don't have to be, though. They don't have to be. Some DSPs have like 256-bit bytes, which is crazy. But in general, it's pretty common for a byte to be 8 bits. I don't think I've ever programmed. No, I've programmed on a DSP once. But, like, if you're talking about normal PCs and things like that, the char is probably going to be 8 bits. Shorts are usually 16 bits. Integers are usually 32 bits. Longs, the long data type, well, that depends whether you're talking about Linux or GNU/Linux, as I've taken to calling it, or Windows. So Windows, a long is going to be 64 bits usually. On Linux, a long is usually going to be 32 bits. Then a long is 64 bits in both. And so, you know how uncertain that makes me feel, knowing that if I take my code and move it to a different system, the size of my integers might change. You know, like, because in theory, you could take your code right now and run it on a different system, and all of your integers turn into effectively shorts. For the maximum value, you know, you have this 16-bit number, right? This is like, 32k to the 15th power? Yeah. So positive 32k, negative 32k and change. So instead of having numbers that go up to 2 billion, all of a sudden, without you changing any of your code, the maximum number is 32,768 instead of 2 billion and change. Do you know how unpleasant that is? How surprising you would be if you moved to a system that had 16-bit integers? So what I do when I'm coding for realsies is I don't use int. I mean, I might use int. If I know the number is going to be from like counting from like 0 to 100, I'll use an int. Who cares? Nobody cares. Right. But if I have to make some sort of assumption about how much range I need, like I'm making a video game and the high score could go up to at least a billion, right? Well, that'll fit inside of an int. I might start feeling a little bit nervous at it because I'm like, well, if you get up to 1 billion, you could probably get up to 2 billion. And if you get up to 2 billion, you can overflow. So I might, at that point, just use a 64-bit integer. You know what I mean? But if I know scores will never go above 100,000, and it's fine. You know, for, you know, as long as it's 32 bits. The better way of doing it is by including student.h, or cstudent, as it's called. And this gives you these fixed bit sizes for the numbers. And what's really cool about that is you'll never be surprised by your integer growing or shrinking, right? Your long won't suddenly change from a 32-bit number to a 64-bit number, or even worse, going from a 64-bit to a 32-bit. If you want a 32-bit number, then you say int 32 underscore t, and you get a 32-bit number. The only downside to this is that the types are like long. I like just typing int. It's 3 letters. You know, it's very fast to type. And so here, I'm showing you how you can actually alias the type so that you can make it smaller. And you need to hashtag include C student, like that. And then, what are you mad about? Oh, yeah, that's part of the assignment. Okay. And so what I'll actually do, like in all seriousness, I wouldn't even say uint64. I'm going to say u64. Okay. And so I'm going to have u64 as an alias for unsigned integer 64. And I'd have maybe like i64 for an int64t. And so this gives you types very similar to Rust, where, you know, you tell it, like, I want a 32-bit integer. I want a 64-bit integer. And you get it. You know, like, you know, always in Rust how many bits you have to play with. And here, you can do the same thing. Three letters, easy to type. You just set up an alias. So instead of having to type unt64_t every time, you just type u64. Nice. Okay. You guys understand this? You guys get it? Makes sense? All right. It's, you know, in practice, it's a really good idea to tell it, I want 32 bits or I want 64 bits. Like, if you need more, you're out of luck. So, could you make it int? It's not going to like that. But you can make it n, or you can make it int with all caps. People are going to love you at the code review if you do that. Capital I int. There you go. People are going to be like, I don't know about this guy. I don't know about this guy. Yeah, in general, I like I64. It's 3 letters. It expresses very succinctly. I have a signed 64-bit integer. Only downside is you lose context highlighting. So you can see uint64t is highlighted in green, but uint64 is not. If you alias something, you lose the nice little coloring. So you probably have to play around in Vim somewhere to set up, you know, syntax highlighting for that. So, yeah, all right. So basically, when we're working with bit fields, we just give a meaning to each one of the bits. Like we saw earlier with the open command, each one of the bits in flags means something different. You know, we're truncating a file, we're appending to a file. Truncating means when you open a file, you delete it. So if you're opening a file for writing, you have the truncate flag set, it erases whatever's there before, and then writes to it, which is the default. Or you can set the append bit where it goes to the end of the file and then writes to the end of the file, which is what you do for like log files and things like that. And so instead of needing 32 different parameters here, you just need 1. Instead of having to do 32 operations where you're copying things around, you do 1. It's really nice. And kind of complicating this is it's a lot of stuff in here. Kind of complicating this. Let's just delete all that. Okay. Is the fact that bits. Well, let's see. How big is an integer? Do you guys think on our system? I've already told you the answer. How many bytes? Size of is a built-in function in C++ that tells you how big a type is. How big do you think that is? It could say 2, but it won't. On GNU/Linux systems, I think it's pretty much standardized that ints are 32 bits. But according to the C++ standard, int, if this returned 2, that would be a conformant. That would be a conformant program. So how big do you guys think a U64 is? This is like the easiest question I'm going to ask you guys all semester. So please, you know, those of you that are like chilling, please chime in on chat. How big is a 64-bit integer? Who's buried in Grant's tomb? If you set a paper airplane on fire, what happens to it? As one of my friends in 8th grade found out. Yeah, it's going to be 8 bytes or 64 bits. Yep. Now, what if we make a variable called Bob's Big Boy? And we make this guy a Boolean. How many bytes does a Boolean take? This is kind of the point. It's kind of the reason. It's kind of the reason why we use a bit set. How many bytes does it take to hold one Boolean? 1 bit. How many bits does it take to hold a bit? Sounds like a trick question, just like the earlier one. Who's born in Grant's tomb? Grant, or who's buried in Grant's tomb, sorry. Who's born in it? I hope nobody. How many bits does it take in C++ to hold a bit? Vote for 2, 1. The answer is 8 bits, 1 byte. Okay. So a bool, which holds 1 bit, takes 8 bits to hold 1 bit. It's not efficient, right? This is not a great thing, right? If you care about memory, like the bool type, yeah, you might as well just use a char, right? Because a char is definitionally 1 byte, always. Char is always 1 byte. Now the trouble with a char, trouble with a char is that, like, let's say that you have char and you're using it as a bit field, and you do something like you set it equal to the ax or something like that, which is 1, right? You like see out, the value of the ax. You want to print out this bit field. Something kind of weird happened. It didn't print out anything at all. You see that? The reason for that is because chars, by default, get output in ASCII. And so it's going to do an ASCII code lookup on whatever your bit field is if you use chars as your bit field. So this is actually one of those sharp edges in C++. A lot of people like using chars as like an 8-bit bit field. You just need a char and you can hold 8 booleans, true or false. But if you ever try outputting it, it does an ASCII table lookup and you get very confused. So, all right, how big is this? Integer x, char y. So this guy here, as you recall, is 4 bytes. This guy here is 1 byte. Luke, what do you think? How big is Bob's big boy going to be here? Five bytes is a very logical, very reasonable response, but the answer is 8. So, what if we added another character? Z. What do you guys think? 6? 8? 12? What do you think? Still 8? 12. What if we put Z down here? Just moved it. Now it's 8. I didn't change which variables we had. I just moved it up. You move it up, it goes from 8 bytes to 12 bytes. What if you put it here? It's still 8. Okay. So the reason why it does this is there's a concept, learning point number 1, data alignment. All data is aligned to memory boundaries that are powers of 2. In a struct, everything is aligned to the biggest member variable. So if you have a int, that's going to take up 4 bytes. And then these guys collectively take up the next 4 bytes. So we've got 8 bytes in our struct. We're only using 6 of it. The other 2 are wasted. And in fact, if I run this code, you'll see it's 8 bytes. And if I erase Z, we're just throwing away one of our member variables. The struct does not change in size. In fact, I could make 4 different chars here, and the size of the struct is exactly the same. because when you have an int that's 4 bytes big, then the thing is laid out in memory in 4 bytes at a time, if you want to think of it that way. So when you put the char above the int, that took up its own 4 bytes. Then you had the int, 4 bytes. Then you had the other char taking 4 bytes at a time. So this is called data alignment, memory alignment. It gets worse, watch this, if we do like a double. So a double is 8 bytes, right? So given what you know now, it's going to be laid out in chunks of 8 bytes at a time. So how many bytes is this going to take up now? It's an extremely inefficient data structure, by the way. That is correctly 24 it is. Okay. But if I move the A to this side, how many bytes is it going to take up now? Everybody. I didn't change the number of member variables, I just moved it around to make it a little bit more efficient. So how many bytes is it going to take up now? $16 is correct. What about a long double? So how does the char know there's an 8-bit or a 4-bit coming next? When C++ analyzes the struct, it actually looks at the whole thing, and then it lays it out in memory according to these rules. Basically, the rule is whatever your biggest thing is, and everything's a power of 2 in size. There's an align command in assembly that says, you know, what power of 2 size each chunk of memory is aligned to, essentially. If you say align, and it's like the log, it's the log base 2 of the size. So like align 2, align 4. It's like the power of 2 of 4, whatever. Yeah. So here we have got a 48 byte. We've got a 48 byte Bob's big boy. We're using 18, and we've allocated 48 bytes to hold 18 bytes. So it is like pretty bad. It's pretty bad. It's almost 2/3 wasted, right? You guys understand? So, and this is true even if we don't have a char, even if we're just using like a bool. So now we're not even, you know, technically we're not even needing, we don't even need the full character, right? Doesn't matter, it's still 48 bytes. Because a Boolean, the minimum you can address on most modern systems is a single byte at a time. So if you have a variable called Boolean B, you get a byte, because that's the smallest you can use to store it into memory and to read it from memory. If you want to be more dense, get 8 times the performance, you can pack 8 Booleans into 1 character, which is what we're going to be doing today. Okay. So we're going to do something called bit packing. Learning point number 3. Bit packing allows you to treat a char like 8 bits or an int like 32 bits. And then that allows you to do 32 operations at the same time, 32 reads, 32 writes, 32 searches, all at the same time. Very useful stuff. So these things are called bit fields or bit sets. And each of the different bits in an int is has a meaning. Like bit 1 is the shotgun, bit 2 is the double-barreled shotgun, so on and so forth. Okay. And so in order to do anything with a bit field, you have to learn the Bitwise operators. So like I said, Bitwise in Fresno, the name of a a tech company that was named after these operations in C++. It sounds cool too, right? I'm bitwise. I'm wise to the bits. I'm not a bit idiot. I'm not bit dumb. I'm bit wise. I'm not bit stupid. So it was a good name. It was a good name for a scam. Okay. I mean, sorry. A real estate company. Sorry, for a incubator, tech incubator. I mean, allegedly. Something. Okay. So for those of you that have not studied the rise and fall of Bitwise in Fresno, you probably have no idea what I'm talking about. But it's this massive amount of drama in the tech community in Fresno. It's really sad because Fresno really needs a tech community. It's one of the reasons why I teach computer science, actually. Because I was like looking around, like, where's the tech community? I'm from San Diego, and it's like there's tech everywhere. Like, where's the tech in Fresno? You know, there isn't any, right? Or they're hidden. Okay. So when you do bitwise operations, you're going to be operating on a minimum of a byte at a time, 8 bits at a time. You can't directly have a variable that holds 1 bit. The minimum you can read and write to RAM is 8 bits, 1 byte at a time. So here we go. Here's bitwise AND. So when you have a bitwise AND, it's a single ampersand, not a double ampersand, which is what you're used to for logical AND. When you do bitwise AND with 1 ampersand, what it does is it looks at each pair of points, and it does an AND on them. 1 means true, 0 means false. So for the first number here, 1, 1, 1, 1, 0, 0, 0, we look at the first bit as a 1, first bit over here, 0. True, ANDed with false is false. And we go through each each pair of numbers. We go through each bit, each pair of bits, and. We're doing a parallel operation. We're doing 8 ands all at the same time in a single cycle. And so this allows bitwise operations to be, in this case, 8 times more efficient in terms of memory and performance than if you add 8 different booleans. If you have an integer that's 32 bits, you can do 32 times the speed. 32 times you can do sets, deletes, and searches all in one operation. It is like logic gates, absolutely. It's definitely like logic gates. Okay, and so let's take a look at this. So switch over to OneNote. So it looks for common values. It has to be true in both places, right? Because and the only way you get a true with and is if they're both true. Okay. So it's going to be bitwise South Stadium. Right. So if you have, let's just do 4 bits at a time. 1, 1, 0, 1, and you AND it with the 0, 1, 1, 0. What you do is you look at each pair of numbers to create the output. Yeah. So true ANDed with false is what? You can multiply them also. Like sometimes people will say that the AND operation is multiply or asterisk, right? So you're literally just multiplying together. In electrical engineering, they draw it as a multiply a lot of times. So true ANDed with false is false. What about true ANDed with true? What about that one? So you look at each pair one at a time. True ANDed with true is in fact true. False ANDed with true, so a true and a false. If you AND those together, you get a false. Very good. And true ANDed with false again is a false. And so the output is this. Now, if you think of these things as integers, you're going to be completely confused, right? Because this number here, this is the 1's bit, the 2's bit, the 4's bit, and the 8's bit. And so what we did is we took the number 13 and we ANDed it with 6 and we got 4, right? Like if you think of these things in terms of the number that they are, it doesn't make the slightest amount of sense. 13 ANDed with 6 is 4. Like what? Doesn't make any sense. You know, what are you talking about? It's true, I guess. I don't know. But you can't think of these things numerically anymore. You have to think of them in terms of like each individual bit. So instead of the 1's bit, the 2's bit, the 4's bit, and the 8's bit, the first bit might be, you guys want video games or operating systems as your analogy today. You guys want video games or operating systems? Fine with both. Both? All right, you got it. So the 1's bit here means that you have the axe. And the 2's bit here means that you have the rocket launcher. And the 3's bit here means you're opening the file for reading. I can't do this. The 8's bit means you're truncating the file. No, I can't do this. We'll just stick to video games. So yeah, the axe, the rocket launcher, single-barreled shotgun, and the sniper rifle. Yep. Stream lagging. Let me decrease the stream quality for you. 1080p. There you go. Okay. So what we're doing in English here now is this is the person's inventory, right? So this is their inventory. They have the axe. They have the single-barreled shotgun. Now let's maybe make it the I don't know, grenade launcher. Why not? Okay. So they've got the axe. They got the grenade launcher. They got the sniper rifle. This command here, this command means drop the axe and drop the sniper rifle. The reason why it means drop is because if you take anything, any value, it's called x, take any value and you AND it with true, you get the original value, right? Because false ANDed with true is false, true ANDed with true is true. So if you ever AND anything with 1, you do nothing to it. But if you AND something with 0, you get 0. And so our input is the items that we had before. And then this here means drop the sniper rifle. This 0 means drop the axe. This means leave the grenade launcher alone. This means leave the rocket launcher alone. Don't drop them. Okay. So maybe I'll start with no axe so we get a little more variety in here. So what we do when we bitwise AND this is that the sniper rifle goes from being true to false. Grenade launcher stays true. The rocket launcher stays false. And the axe, we try dropping it, but it's already gone. We don't have the axe. So we don't have the axe now either. So this was our before inventory. And then our after inventory is the same, but with the sniper rifle gone. You see how that works? So this command here, what we did here was to give a command to drop the sniper rifle and the axe in one operation, one cycle. It's extremely fast, very efficient, very compact in memory as well. So if we want to pick up an item, then we use bitwise OR. Okay, let's go back to the presentation. Bitwise OR uses the single vertical slash. Bitwise AND is single ampersand. Bitwise OR is single vertical slash. When you do the single vertical slash, what you do is you take each pair of bits and OR them together. So the rule for OR is that if one or the other or both is true, the output bit is true. So 1111, 0000, ORed with 0000, 1111 is all ones because you go through each pair of bits at a time. So the you can either go front to back or back to front, doesn't really matter. So it's going to OR together that bit and that bit. So true ORed with false is true. Okay. And then we do true ORed with false is true. And you just run down the line. Okay. And so if you have 1101 ORed, that OR looks just like a 1, unfortunately. Or, I don't know. No, now it just looks like a 1. I don't know. I have no idea. Okay, so if you OR it with 0110, true ORed with false is true. True ORed with true is true. False ORed with true is true. True ORed with false is true. And so what this means in English is pick up, what do we have before? Pick up the grenade launcher, pick up the rocket launcher. So if this is what we had before, if we bitwise OR it with this thing here, what we're saying in plain English is pick up the grenade launcher and the rocket launcher at the same time. So what you can do is when you have an inventory bag dropped on the ground, it can have a bit field of all the weapons in the backpack. And all you have to do to pick up the entire thing is you say, my weapons are going to be bitwise ORed equals with a backpack. So if that's a bit field and that's a bit field that both hold weapons, then you just say weapons vertical slash equals backpack, and voila, you have now picked up all the items that were in the backpack. Simple as that. Yep. So one operation and you pick up every weapon in the backpack, assuming that your backpack can't hold more than 32 bits. All right, so let's do the operation here. So we've got, as our input, our current inventory, we've got the sniper rifle, we got the grenade launcher, let's clean that a little bit, sniper rifle, grenade launcher, we got the rocket launcher, we got the axe. And we are picking up the grenade launcher and the rocket launcher. So let's do this together. True ORed with false is what? What is true ORed with false? It is true. And then true ORed with true is what? Also true. And false ORed with true is what? True. Good. And false ORed with false is what? False. Okay. The rules for bitwise or in general. Anything ORed with 0 gives you the original item. Right? If it was true before, it's true after. If it was false before, it's false after. And 1, anything ORed with 1, I should say. X ORed with 1 is equal to 1. So anytime you OR something with true, the output is going to be true. Doesn't matter what the input is. Just like how if you AND anything with false, you're going to get false. If you OR anything with true, you're going to get true. Doesn't matter what the input bit is. Okay. And so if you compare our inventory before and after, before we had the sniper rifle and the grenade launcher, we gave a command to pick up the grenade launcher and the rocket launcher. Well, we already had the grenade launcher, so nothing happened there. We still have it. And then we now have the rocket launcher. We have this, whereas before it was false. Cool. Easy. Okay. So OR is used to pick things up, and is used to drop things. It's also used to select things, search for things. And we're going to learn bitwise not in a second. Bitwise not, any bit that was true becomes false. Any bit that was false becomes true. And you do a bitwise not by using tilde. So if you put a tilde in front of an integer or a char, then all the true bits become false bits, all the false bits become true bits. And we can turn off a single bit by ANDing something with the not of that bit. So X here is 1, so it's the ones bit. We bitwise inverse it, which turns it into all ones, but a 0 in the 1 spot. And then we AND it with Y, and then that 1 spot 0 turns into a 0. Everything else is left behind. That's how you drop items, technically. You AND it with a bitwise not of something. And we'll go over those operations in a little bit. XOR is pretty cool. XOR is a weird one because it's reversible. So XOR is like OR, except the rule is if you have X XORed with 0, you get X, it does nothing. If you have X XORed with 1, you get the not of X. So it flips the bit. So the 1 bit, when you do XOR, means flip it. Change it from true to false or false to true. If you XOR anything with 0, that means leave it alone. So XOR is really cool because it allows you to do cryptography. If you have a secret message, now instead of it being an inventory, this is a secret. And this is something called a one-time pad. Here, this is your secret message. Right? You're an agent working for the KGB, and you've got a secret message of 1100 that you need to send back to headquarters in Moscow. Before you left for Fresno, they handed you something called a one-time pad. And so what you do is you cross off letters from the one-time pad, giving you essentially 8 bits at a time. And you XOR, instead of OR, we're going to be doing XOR, which looks like a caret, not exponentiation, not exponentiation. It's XOR. You cross off one byte at a time, and 8 bits at a time. And then anytime you have a 1, you flip the bit in your original email. Anytime you have a 0, you leave the bit from your original email. Thus, it is exactly 50-50 for somebody who doesn't have access to this. Every time they see a 1, it's a 50-50. It's a 1 that's supposed to be there. Anytime you see a 0, it's a 50-50. That 0 is supposed to be there. So you have no information about the of the contents of the email to begin with. But when it arrives, XOR, because it's reversible, right? If you look down here, anytime you have a 1, you flip the bit. That means you can flip it back. 0 leaves it alone. 1 will flip it back. So if you apply XOR twice to the same operation, you get the original thing back. And so this is what we're going to send out. This is our encrypted version here. This is our encrypted version. This is what's going to get sent out over the internet. So we take true, XOR with false. So the rule for XOR is that it can be true or false, but not both. So one or the other is true, but not both. So 2 falses gives you false, 2 trues gives you false, 1 true gives you true. So here we've got 1 true right here. And so true XORed with false is true. True XORed with true is false. Or you can think of the 1 as meaning flip the bit here. So that 1 becomes 0. So true XORed with true is 0. False, whatever, however you're going to put it. False XORed with true is true. False XORed with false is false. Now if we XOR it again, so now we're in Moscow, right? So this is out in like Langley in America. They're sending a secret message back to Moscow headquarters. So they're going to do the exact same operation. It's the same one-time pad. So as they get a message from you, they cross off 1 byte at a time, 1 character at a time, and use that to generate the one-time pad. So 0, 1, 1, 0. And the result here, true XORed with false, true. False XORed with true, true. True XORed with true, false. False XORed with false, false. And so what we ended up with, this is our original message here. We ended up with the original message again. So we started with the original message. We used the one-time pad to encrypt it. We send this out over the internet. This one here goes over the internet. When it arrives in Moscow, they use the one-time pad to decrypt it, and then they recover the original message. So that's cool. So one-time pads are provably unbreakable technology. You cannot break one-pad time encryption, except we have, of course. So there's actually a couple ways you can break one-time pads. The easiest way, so to speak, is just to break in physically. Like somewhere they're going to have the one-time pads like in a journal or something, you know? And so if you just break into the secret agent's house and they've got they got like a book or something, you know, and the book's got their one-time pad in it, you just photograph it all, take a picture of each page. And then as they cross off characters, you know which characters they're crossing off and you can decrypt it too. So, or, you know, slightly more difficult, you break into KGB headquarters, right? And copy all of their one-time pads out of their vault there. Yeah, it seems harder to do that one. The harder way, though, of breaking one-time pads is what the United States did during the Cold War. The Russians generated tons of code pads during World War II. They had a giant room filled with people randomly typing characters. And the people would start off being very diligent. I'm going to pick a P, then I'm going to pick a B, then I'm going to pick an and, then I'm going to pick a J. Oh, dang, I'm hungry now. You know, PB&J. What? And then after like 10 minutes of their 16-hour shift, they're just hitting random keys. But here's the thing. If you're just hitting random keys on your keyboard, they're not going to be random, right? And so the Americans we're able to grab the names of some very high-level spies by decrypting these one-time messages. So, for example, Harry Dexter White, who was the Undersecretary for the Treasury under Morgenthau, founder of the IMF, the International Money Fund, he was a Russian spy named Jurist, right? And we know this because these unbreakable, technologies were broken. Because if you know which keys they're going to hit, it's not random anymore. You've got information. You know they're going to be typing ASDF, over and over again. And, it does take some computational power to try all the different possibilities. It could be A, it could be S. You have to try this for each one of the letters, see which ones, work out, And it's the kind of thing the NSF is really good at. So, yeah, XOR is really useful for cryptography and random number generation, things like that. All right, so next up is bitwise shifting. So if you use double left arrow, you can take a number 1 and left shift it a couple times. So if you left shift the number 1 once, it turns into number 2. If you left shift the number 1 twice, it goes 1's bit, 2's bit, 4's bit, 8's bit, 16's bit. Every time you left shift, you're doubling the entire number by 2. Every time you right shift with double right arrow, by the way, the CN and COUT operators, the stream extraction, the stream insertion operators, which use double left arrow, double right arrow, these are actually bit shift operators, okay? And so C purists actually hate the fact that Bjarne, to this day, they get mad that he used the left shift and the right shift operator to indicate print and read from the keyboard. So they're still mad about that. Now, if you want to see if a bit is set, use ampersand. So if weapon ANDed with weapon X. So weapon X is 0, 0, 0, 0, 1. So if you AND something with the axe, all those zeros turn into zeros, and the 1 leaves behind whatever was there before. So if what was there before was a 0, you don't have the axe. What was there before is a 1, you do have the axe, and it'll print, and my axe. If your weapon bit field has the single-barreled shotgun, it'll print out, you have the single-barreled shotgun. Yep. This is how people write code all the time. It's called a bit field. This is how you can set things. You can set things using bitwise OR. I'm going to pick up the axe, rocket launcher, and whatever that is. And if you want to drop something, you say you ampersand something and something with the not of it. Because if axe is 1, if you do bitwise not on 1, it goes from all zeros in a 1 to all 1s in a 0. So if you AND something with a not, then you drop it. So let me show you guys what that looks like. And then we'll be done for the day. So we've got this bit field here. Let's just clean up the right down here. We're not doing crypto anymore. Okay. Boop. So we want to drop the axe, let's say. Let's give us the axe, just to make it a little easier. If you don't have the axe and you try dropping it, you just don't have the axe, but it's not very exciting. Okay. This is our inventory, and this is our command. And so we want to drop the axe. So what we say is we say weapons is equal to weapons ANDed with the not of X. So this is X here, this is weapons. And so if you not X, then all those zeros turn into 1s, all the 1s turn into zeros. So when you not X, this becomes 1, 1, 1, 0. And then when you AND it with these guys, all the 1s, remember, if you AND anything with true, it stays the same. So we're not going to touch any of the rest of the bit field other than the one that's 0. So true ANDed with true is true, true ANDed with true is true, false ANDed with true is false. See, we got 1, 1, 0, whereas before it was 1, 1, 0. And now for the last one, we have a 0 here because we ANDed it with a not of X. X is 1. So that bit is the only one that's going to be false. When you AND it with 0, then that thing turns into 0. And so here is our output. As far as before, we had 1101. Now that we've dropped the axe, we have 1100. We do not have the axe anymore. Now, if we didn't have the axe to begin with, we'd still bitwise and it, and we'd still not have it afterwards. And that is how you build Bitfield. Yep. There's a more professional version of this in the standard library, which is called Bitset. That's the C++ version of it. But a lot of the times, you don't need a Bitset. The ultimate data structure that you guys need for a lot of these things is called int. And with that, I'll say goodbye to you guys, work on Gilded Rose for the remainder of the hour, and not and will be 1 and be 0, sort of like an anti-OR, yeah. So what was true before, like we knotted it with axe, right? Axe was 1 before, so it turns into a 0, everything else turns into a 1. All these 1s do nothing, so they leave the rest of the inventory alone. When you AND it with that 0, that bit turns off. And so you can selectively turn on a bit, turn off a bit, and test a bit to see if it's there. And you can do this 1 bit at a time, or if you're a super cool pro gamer, you could set 5 bits at a time, 32 bits at a time if you really want to be wild, and be much, much faster. All right, so that's it for today, guys. Thanks for coming out. Hope you enjoyed our adventures in Bitsets and Bitfields. If you need help with Gilded Rose, message me now. I'll be standing by. Peace.